Okay, so this is then the acceleration required practical. And what we're going to be doing in this is we're going to be talking about two things. We're going to be measuring the effect of the force, and we're also going to be measuring the effect of the mass on the acceleration of a toy car. Now, it's a little bit complicated, this, and there's quite a lot of thinking, and there's also quite a number of things that could actually be changed throughout the practical. So what I'm going to do is I'm going to kind of talk as like a general thing, but you need to also be thinking about in the back of your head what could actually change in addition. So measuring the effect of a force on acceleration at constant mass. Right? So use the ruler to measure intervals on the bench. So what I've got here is I've got a ruler, right? And what I can do then is I can measure intervals on a bench, on a runway, on a track, whatever it may well be. So it could be 0.2 meters, 0.4 meters, all the way down to a meter. Attach the bench pulley to the end of the bench. That's here, that's the bench pulley. Tie a length of string to the toy car or the trolley. So what we've got then is we've got a piece of string that goes all the way along over the edge of the pulley to the weight stack. Attach the weight or the full weight stack, which is 100 grams, which is then 1 Newton, to the end of the string. Then what you need to be doing is you need to kind of getting yourself set up so you can look at the results that are then going to be appearing. If I just skip out number 5 to start off with, what you're going to need to do somewhere is you need to have a stop clock. Right, now the best place for a stop clock is right in the middle, but make sure it doesn't affect or so you can't see anything. So maybe behind the piece of string. Then what you're going to be doing is you're going to be recording your results on a mobile phone. So what you can do is you can actually set the whole experiment going, and then you can do like a pause and slow motion or whatever it is on mobile phones, right? It's all beyond me. And then what you can do then, you can pause it at the correct places. So if you're then doing 0.2 or 20 centimeters, what you can do is you can pause it when the car gets to that. You know it's at 0.2 or 20 centimeters, and in the background, what you can do then is you can see your stop clock. Record the results in a results table, and then what you do then is you repeat the whole process, changing the weights. So you might go from 100 grams to 80 grams to 60 grams, which then affects the amount of newtons. So 80 grams will be 0.8 newtons, 60 grams will be 0.6 newtons. Now, when you actually take the weights off, and this is kind of one of the weird things with it is, if I take off 20 grams, what I've got to do then is I've got to transfer those 20 grams onto the toy car to keep the mass of everything the same. Then on your results table, you're going to calculate the speed and then the acceleration. Right, variables. Before I start talking about the actual results table, so don't mess. So the dependent is measure. So during the practical itself, I'm measuring the time using my stop clock. In class, independent change. What do I change between experiments? I change the weight, right, which is the weight stack off the end. Then the control is then the mass of the car, the string, and the weight stack all stays the same. The person also stays the same. Now, the results table. Now, there's a number of ways in which the result table could be sort of presented, right? So what I've got here is I've kind of got two results tables. If I do the experiment start off with, right, I can then change my force. Well, I've got my force of 1 Newton for each one of those first 3 experiments. And I've got a distance in meters. But really what I should also do is I also have a force of 1 Newton for 0.8 and 1 meter. Using my phone, I can then work out the time. From that, I know that the start speed is 0 because it's at stationary. Then I've got to work out my end speed. And to work out my end speed, I'm going to use speed equals distance divided by time. So my end speed equals the distance divided by whatever the time on the phone said in seconds. That will then give me my end speed. Then what I need to do is I then need to work out my acceleration. And my acceleration is change in velocity. So it's my end speed, which is there, take away my start speed, which luckily is 0, divided by the time taken. That'll then give me my acceleration. Now, what I've then done is I've then done 0.8 newtons, and I've then done it for the same distance. Then theoretically what you should then do is then maybe do 0.6 newtons and do it for all the different distances. You just got to look at in the actual exam itself what they are changing, right? Whether it's the force or the distance, you know, there's a lot of different permutations to it. Now, in conclusion, what would we see? Right, we've got acceleration at that side, we've got force along that side. Okay, we've got both of those in our table. You plot a line, and what you'll do is you'll get a nice straight line. And in a nutshell, what happens is, as the acceleration increases, or as the force increases, the acceleration increases. Right, it's a line of best fit, but the acceleration is directly proportional to the force, which means it's your straight line. Okay, it's directly proportional to the force. The second experiment is where we're then looking at the mass. So it's the effect of the mass of the car on the acceleration, and this time with a constant force. So put 200 grams on top of the car, right, or a trolley. Now you've also got to remember that the actual total mass, again if they ask about it, is not just the mass on the car, but it's also the mass of the car. So we could have on the car, of the car, the string, and the weights, right? Ultimately, that is the actual total mass of the whole system that's then getting moved. So what you do is you hold the car at the starting point, attach your chosen weight stack to the end, right? So what I would do is I'd put 100 grams, which is then your 1 Newton. Release the car at the same time as you start your stop clock. You've got your stop clock sat there behind, you've got your mobile phone, right, and at intervals, just like you did before, 0.2 meters, 0.4, 0.6, etc., etc., you then do exactly the same thing as you did before, where you're going to look at the distance and you're going to look at the time on your stop clock. Now, the repeat on this is then increase the masses of the car. So what you could do is you could add on 50 grams. Okay, and then repeat the experiment again. This is then the results table, right? So what I've done is I've started off with 200 grams on top of the car. I've got my distance, and theoretically I then should go up to 0.8, I should go up to 1 meter, I could have done 0.3. I then measure the time taken in seconds, which is what I'll then see on my mobile phone because I've recorded it. I've got my end speed, and I can work out my acceleration as I did before. Then the second part of the experiment would be then to increase the mass, maybe 250, then maybe 300, right? Again, it depends on the question itself, right, on the exam, but you've just got to know the principles that you're increasing the mass. The variables, right, don't mess is the time, so what you're measuring. In class, what you're changing between each one is the mass of the car. And then things that you're keeping the same, in particular, is the weight, which is the weight stack on this end, must stay the same. Now your graph looks differently this time, right? As the mass increases, which is going that way, the acceleration decreases. So the heavier the car in grams, the slower the acceleration, which kind of makes sense. What you do is you get a curved line of best fit. If you're asked to do a line of best fit, make sure that you look at it, and if you can see that it looks like a curve, the chances are it is a curve. This time, acceleration is inversely proportional. So it's not directly proportional, which is a straight line. It's inversely proportional, right, to the mass. So if you're asked about it at all, where what happens with the mass and the acceleration, you would then say it is inversely proportional to the mass. Now that's quite complicated because what you've got is you've got two methods, right? You've got two methods. One is changing the force, one is changing the mass. You've also got two equations, right? You've got your speed equation and you've got your acceleration equation. Acceleration equation. Can't read that, but that's what it says. All right? And then you've also got graph drawing. And you've got to remember your conclusions is for the force one, directly proportional. For the mass one, inversely proportional.